Hi everyone, we're here to do the third video in the introduction to Fermat's last theorem before we get into the nitty-gritty. And I decided instead of starting with a basic introduction to elliptic curves, I would start with how we get from Pythagoras to elliptic curves. And then once we have that, we'll understand what are we even talking about. Why did Wiles prove all of his machinery using elliptic curves and modular forms in order to get back to Pythagoras's theorem. So we're going to start with the Pythagorean theorem, which everyone surely knows. And then the question is, how are we going to get from there, which that means that a right triangle with sides A, B, C, a squared plus b squared equals c squared, right? How do we get from there to an elliptic curve which looks something like this? There's varieties, it can be, there can be coefficients here and extras and so on, which affect the shape of it. But this is a basic form of the equation for an elliptic curve. An elliptic curve looks like there's one of two basic shapes. It can either look something like this or something like that. And this is all stuff, I don't know a lot more about this yet. That's what we're going to get into. But this is the Pythagorean theorem. This is the basic equation for a elliptic curve. And today I'm going to show us how to get from here to here. So the Fermat's last theorem is that while that's true, a to the n plus b to the n equals c to the n is not true when n is greater than 2. These can be integers or rational numbers. These obviously are integers greater than 2. And this is what I'm sure we've all seen before. This is the famous theorem, okay, that we're trying to prove. So to begin with, though, we need to get from here to here. So if the first thing I want to do, this is just a bunch of algebraic manipulation. It's not very hard. There's nothing complicated about this. It's just algebra. But we all know the most famous answer to this is 3 squared plus 4 squared equals 5 squared, right? That's 9 plus 16 plus 25. Another example is 5 squared plus 12 squared equals 13 squared. 25, 144 is 169. Then another thing is you can divide through by the right-hand side. So you could take 3 squared over 5 squared plus 4 squared over 5 squared equals 1, right? And then that's the same as 3/5 squared plus 4/5 squared equals 1. Okay, so all of these are examples. These obviously are rational numbers. These are rational numbers too, but these are integers. But it's very easy to go back and forth between a more general answer where A, B, and C are rational numbers to integers. So we're really working with rational numbers in order to get the 1 over there. Okay, let's move to another page. So the Greeks and ever since then have asked a lot of questions about these equations. And one that they asked is called the congruent number problem. Congruent numbers. What that means is, what rational numbers can be the area of a right triangle with rational sides. Okay? Any number that fits this is called a congruent number. So, for example, 6 is one, because we have our one answer, 3 squared plus 4 squared equals 5 squared, so the triangle 3, 4, 5. So the area of a triangle is 1/2 base times height, right? How do we get that? The sides here are 3 and 4. If we just draw a rectangle, then the sides here are 3 and 4, right? So the sides of the rectangle are 3 times 4 is 12. If you divide that by 2, it's 1/2. So the area of this triangle is 1/2 3 times 4 equals 6, okay? So 6 is a congruent number. The question we want to answer is 1 a congruent number? Now again, it's an interesting question, but we're not necessarily interested in this question ourselves. What we are interested in is how can we look at this question and what kind of manipulations can we do in order to get to an answer to this. And as you'll see in the process, we're going to end up with an elliptical curve, with an elliptical, the equation for an elliptical curve. So, okay, so that's what we're looking for. Let's go back a minute to the Pythagorean theorem. And if we have, as I said, if we have a squared plus b squared equals c squared, we can divide through by c, and we end up with a over c squared plus b over c squared equals 1. Does that remind you of anything? That is the equation for a circle, right? With x equals a over c, y equals b over c. And this is the radius squared, so what we have is a unit circle. So if we have a point xy up here, then we're looking for points xy that are rational, okay? If we draw a line through these 2 points, we have a line with some slope that crosses the circle, intersects the circle in 2 places, at -1, 0, and at x, y, right? What is the equation for this line? Well, the general equation for a line is y equals mx plus b. Remember, the slope is the rise over the run. The rise here is y. This little piece is x, but this little piece is 1. So this here is x plus 1, right? So the rise over the run here is y over x plus 1. Y over x plus 1 equals t. That's the slope. This is the equation of this line. It looks a little different than this, but all we have to do is multiply by x plus 1. So y equals t times x plus 1, or tx plus t, right? Same equation. Okay. So we have that now. So the slope of this line determines this point. Conversely, this point will determine the slope of this line. What this means is, if the slope is rational, then this point has to be rational. And if that point's rational, then the slope has to be rational. So if we can plug in a rational number for t, we should be able to come out with a rational point, which will then be a solution to x squared plus y squared equals c. So the next thing to do is we need to manipulate this so we have x and y in terms of t. Now, in order to do that, we're just going to, we have two equations. We have x squared plus y squared equals 1, and we have that y equals tx plus t. If we just put those together and solve for those two equations, we should be able to find what y and x will equal in terms of t. So let's do that now. So we have two equations, x squared plus y squared equals 1, and y equals tx plus t. Well, this is easy. We can just plug y into this. So plugging this into this will end up with x squared plus tx plus t squared equals 1. Okay? Again, what we're looking for is we're trying to solve for x and for y in terms of t. So let's just expand this a little bit. So we have x squared plus t squared x squared plus 2t squared x. Is that right? 2t squared x plus t squared equals 1. Okay. Let's move the 1 to the other side. X squared plus 2t squared x plus t squared minus 1 equals 0. Now, if we, let's just gather terms now. So here, if we take out the x, we have 1 plus t squared x squared plus just t, there's nothing really new there, 2t squared x plus t squared minus 1. How about that? Didn't really do anything. So now let's get this. So it's just a 1 in front of the x. So we'll divide through. So we have x squared. We're dividing through by 1 plus x squared plus 2t squared x over 1 plus t squared plus t squared minus 1 over t squared plus 1, whatever, the same thing, equals 0. Okay? Now, what can we do next? That's a good question. I forgot. Okay, time for a little edit here, huh? Oh. So now, what do we have here? We have a quadratic equation, right? This is an equation in x squared x, and x to the 0. It's a quadratic equation. That means we know there's going to be two solutions. We could use the quadratic equation, but that would be ugly. Or what is it? B squared minus 4ac over 2a. We don't want to do that. But if we remember, what we have here is we know this point is on the circle, right? So that means that one of these factors has to have minus 1 as a solution. So that means if minus 1 is a solution, then one of the factors is x plus 1. And one of the solutions is x plus 1. So what's the other solution? Well, it has to be this times something to equal this. Well, that's easy. It's just t squared minus 1 over t squared plus 1 equals 0. Okay? So these are the two factors that will solve this equation. So now we have that x is either minus 1 or x equals, we can just flip this around so it's 1 minus t squared, right? If you multiply that by minus 1 over t squared plus 1. It'd be minus t squared plus 1, so I just rewrote it. So these are the two solutions for x. Now, are we getting anywhere? So, next, now we can plug this back in up here and get an equation for y. So we have that, we already know that y equals tx plus t. So just plug this into here. We have y equals t, 1 minus t squared plus t. So if we, the next thing to do is make a common denominator here. So we'll multiply this top and bottom by t squared plus 1. Right? That's 1, no problem. So if we multiply that through, we get t minus t cubed plus t cubed plus t. So these go together and these all go together. Cancel these and we end up with 2t here. So y equals 2t. Okay? So we have x equals this and y equals this. Let me write that on the next page. X equals, make sure we get it right, 1 minus t squared over t squared plus 1, y equals 2t. Now, have we accomplished anything? Let's go back to what we were supposed to be doing originally. So first, we did accomplish what our sort of sub-goal was. Now we have x and y in terms of t. So actually, before we move on, let's look at that. So now we have a circle here. For any t, we'll come out with a point, x comma y, on this circle. So if for any rational t, we can now come up with a rational x and a rational y. And you can see that no matter what t is, we're just squaring it. The x is gonna remain rational, y is gonna remain rational. So anything we plug in, we now will get an x and y on this circle. So for instance, if we do t equals 2, we have then that x equals 1 minus 2 squared is 4 over 4 plus 1 is 5, and y equals, wait, I did something wrong. What do I have wrong here? This must also be over 2t squared, right? Yes, of course it is. Look, it's 2t over t squared plus 1, okay? So it's t squared over t squared plus 1. All right. So y is 2t over t squared plus 1. So that equals 4 over 5. So we came up with xy equals minus 3/5, which the circle is symmetrical. So this is a solution to the Pythagorean equation, as we already know. So 3/5, whether it's minus or not, it's squared. That's going to make it positive. Plus 4/5 equals 1, right? We already know that. Okay, that's interesting. So if we put in something more interesting for, t, then we can get more interesting other values for the Pythagorean equation. And actually, the line sweeps through. As the line sweeps through from this way down to here, you can hit every single rational point on this circle by having rational slopes of t. Okay? That's all very good. But what was our original problem? This is helpful. But what we're actually looking for is whether 1 equals, whether 1 can be the area of this, of such a triangle. So we had that, we started with x equals a over c, y equals b over c. So if we just multiply by c, we have that a equals cx, b equals cy. Okay, so then if we plug these back into the equation, we get into the area equation, we get 1 equals 1/2 cx cy. 1 equals 1/2 c squared xy. Now, if we plug in our values in terms of t for x and y, we get that 1 equals 1/2 c squared x, which is 1 minus t squared over t squared plus 1. Y is 2t over t squared plus 1. So first we can immediately cancel the 2's. And what do we have now? We have something that looks really ugly, right? 1 equals c squared over, this is squared, t squared plus 1 squared times t minus t cubed. That looks vaguely familiar. I think we might be getting somewhere. So let's turn to a new page. So we have 1 equals c squared over t squared plus 1 squared times t minus t cubed. Is that right? Yes. Okay, so we have 1 on this side. Let's multiply both sides by the reciprocal here to cancel that. And we end up with t squared plus 1 over c squared equals t minus t cubed. Okay, now let's do some relabeling and see what happens. This is squared. Let's make that y. So let's use capital Y equals t squared plus 1 over c. Let's make x equal minus t. And then if you multiply all of this through, it looks ugly, but this means that t is minus x, so it's minus x minus x cubed. Minus x cubed is still minus x cubed, so minus minus is plus, that's minus. So you get, if you plug these two in, you get y squared equals x cubed minus x. There we go. that is the equation of an elliptic curve. Now, for our purposes, the only thing that I wanted to do with this video was show us how to get from the Pythagorean theorem to here. We've done this now. It's all about finding congruent numbers. Although I think there are more connections than just that. But what I wanted to do here was demonstrate that there is clearly a relationship between this a squared plus b squared equals c squared and elliptical curves. This particular one is used where we're going here is to prove that there are no solutions where x and y are rational that have an area of 1. But I'm going to stop it here because that's a separate question that we could talk about for another hour. The point here is now you can see, all right, Pythagorean theorem, there is hidden in there. If you just do some simple algebraic manipulations, you can end up with an elliptic curve. What we can do now is all of the studying that they've done with elliptic curves over the last 100 years, we can use that to see what we can get to. So now that we understand why are we even talking about elliptic curves, I'm going to stop for now. The next video will be just a very, very basic understanding of elliptic curves. The video after that will be a very, very basic understanding of modular forms. Then I'm going to go through basically just a brief history, because every video has to have the brief history of the proof, and then what my understanding of the proof is so far. Once we're done with that, we're ready to go, ready to dive into elliptic curves. That'll be the next thing that we do. Okay, thank you for watching. Please leave comments and subscribe and join me on Patreon. Thank you.